So, the unspoken assumption is that the classic load balancers, the pre-2016 ones, would struggle with larger volumes. Jeff Barr hints as much. In some situations, such as instantaneous failover between regions or extremely spiky workloads, we have worked with our customers to pre-provision ELBs in anticipation of a traffic surge. The NLB also preserves the IP address of the client initiating the connection and provides a static IP address for each of the AZs over which it operates. These two features prove extremely helpful. Let's reflect for a moment on the fact that those two features are somewhat in tension. On the one hand, the NLB is akin to an American Black Hawk, the stealth helicopters. It obviously balances the load, it's a middleman between the clients and the back-end servers. However, it can preserve the source IP address. We know this because Jeff Barr writes that with the network load balancer, the original address and source ports for the incoming connections remain unmodified, so application software need not support X forwarded for, proxy protocol, or these other workarounds. Also, Pratibha Suryadevara states that the NLB is a complete pass-through device. We actually preserve your client IP and send it back all the way to your targets. So, the NLB is very classy. Unlike OFISH ALBs or classic load balancers, which stop the packet in its track and stamp their own source IP address on them, the NLB unobtrusively alters the course of the packet. The source IP address is preserved. And this preservation has various benefits. In the video description, the quiz questions will help you explore those. So that is the first feature, the preservation of the source IP address. This is about NLBs being non-obtrusive. On the other hand, NLBs distinguish themselves by having a real presence. Your NLB can have a static IP address. It's important to note that ALBs could not have a static IP address. In fact, NLBs really come to the rescue of ALBs here. You can't assign a static IP address to an application load balancer. If you need a static IP address for your application load balancer, it's a best practice to register the application load balancer behind a network load balancer. That's the AWS Knowledge Center speaking. So you make the ALB a target of the NLB. The NLB cares for the source of the client in two ways. First, it preserves the source's address. Second, it provides a static IP address which the source can send its traffic to. Black Hawk. The AWS NLB is reliably reachable and utterly unimpressive. Unimpressive, the source IP address is preserved. It leaves everything as it is. Reliably reachable, it does provide a static IP address. We're told each network load balancer provides a single IP address for each availability zone in its purview. So multiple IP addresses. If you have targets in US West 2A and other targets in US West 2C, NLB will create and manage two IP addresses, one per AZ. Connections to that IP address will spread traffic across the instances in all the VPC subnets in the AZ. The key word here is static. Classic load balancers and ALBs do use IP addresses. However, the IP addresses for classic load balancers and ALBs change over time. Avoid using this information to statically configure your applications to point to these IP addresses. The AWS Knowledge Center. At this point, we need to sharpen our concept of an elastic IP address. Note that 1. If some IP address is an elastic IP, then it is a public address. 2. If some IP address is an elastic IP, then it is a static IP address. So to be clear, an elastic IP is just another example of a public IP address. Of all the public IP addresses, there's a special subset called elastic IPs. Furthermore, note that an elastic IP address is static. An elastic IP address is static. This must be stressed because most people intuitively associate elasticity with change, and this causes them to believe that an elastic IP address is an IP address that changes. But this is not true. One of the virtues of EIPs is that they remain the same. They are static. There is already an established term for IP addresses that change. Perhaps they are dynamic. The reason EIPs are called elastic is that they are portable. They can be moved from one instance to another, one EC2 instance to another. EIPs can be reused. The term elastic in AWS. A number of products sold by AWS have a name which includes the word elastic. I count 12. We have Elastic Compute Cloud, 2006, Elastic Block Store, 2 years later, Elastic Load Balancing, 2009, Beanstalk, 2011, Transcoder, 13. Both ECS and Lambda came in 2014, but only ECS has Elastic in it. We got lots of Elastic things in 2015, the Elastic Search Service, which has now been deprecated, the Elastic File System, and the Elastic Container Registry, 2015. Then in 2017, we got the Elastic Kubernetes Service. In 2018, we got Elastic Inference. And in 2021, we got Elastic Disaster Recovery. We also have Elasticache, announced in 2011, which offers customers a controllable migraine. A number of entities or constructs feature the word elastic. So these are not exactly services, but features or entities, constructs within services. So we have the Elastic Network Interface, the Elastic Fabric Adapter, the Elastic Network Adapter, ENA, Elastic IP address, and an Elastic Load Balancer, which is a construct but also a service. We can ask whether there is something which all the above services and entities have in common, which is lacked by names lacking the word elastic. I do not think we will locate such a thing. One reason for including the word elastic in the above names is that the expression which is formed becomes a unique compound, such as ECS. This provides a unique name, which has more utility than the generic container service, for example. Elastic has come to be associated with AWS simply in virtue of the word elastic being constantly conjoined with AWS products. However, the above reasons also apply to the word simple, which is found in at least 6 services, and the word cloud. Although the last time simple was utilised seems to be Simple Email Service, announced in 2011. But still, to say elastic is constantly conjoined with AWS product names doesn't get to the heart of it. We can ask, what idea was elastic originally intended to denote? I believe that the word elastic has 2 distinct senses within the AWS community. They can be summarised as portability and autonomy. Portability, moving about, and autonomy. In everyday life, the adjective elastic is understood as an adjective which primarily describes materials with a few derivative senses. Your auntie, who's a nurse, will tell you that arteries and human skin are elastic. Your cousin will tell you that prices can be elastic, and that if Coca-Cola increase their prices by 10%, then the number of consumers demanding Coca-Cola will drop somewhat proportionally, such that we say that Coca-Cola is an elastic good. But smokers are so addicted to cigarettes that if the tobacco companies increase prices by 40%, the drop in demand won't be proportional at all, making cigarettes an inelastic good. Your uncle will tell you that his waistband is elastic. Your younger brother will has an elastic band and your sister a balloon. So in everyday life, the idea involves a single item expanding and contracting. Specifically, the material can store the energy and spring back on its own. Note that collapsible telescopes and clay are not elastic, even though they can be collapsed and moulded respectively. In physics, elasticity is talked about in contrast to plasticity. Elasticity is the ability of a body to resist a distorting influence and return to its original size when that distorting influence is removed. Springs are in this sense elastic. Plasticity is manifested when objects are deformed and they just remain deformed. Then there are elastic collisions in physics as well. A collision between two bodies is elastic if, and only if really, the total kinetic energy of the two bodies remains the same. That's rare. Usually when two bodies collide, some energy is converted into heat and noise, so it's not elastic. If two billiard balls hit each other and collide, each ball will likely have some kinetic energy as they travel away from one another, but a sound will be made. Think of two snooker balls hitting one another. Small sound will be made, and so some kinetic energy is actually converted off into sound energy. So the two billiard balls experience an inelastic collision. Summarising, we have elastic materials, which are deformed temporarily, and collisions. Elastic collisions are those in which the total kinetic energy is retained. They just bounce off each other. It's an idealisation, but the two colliding bodies just bounce off one another, and they are travelling at the same speed with the same kinetic energy as they originally had. These two senses are found in the world of AWS. The relationships among the majority of AWS resources involve CAT-AS, containment, attachment, association. I think of there being an order amongst them. From certainly not commutative, meaning reversible, all the way to almost certainly commutative, meaning reversible. So just to explain those terms, in mathematics or arithmetic, addition is commutative because 3 plus 5 is the same as 5 plus 3, but subtraction is not. So remember, CAT-AS contains, is associated with, cat contains attached cat and then associated with. Contains, well, that's very much an asymmetrical relation. If X contains Y, does Y contain X? Definitely not. When we get to attachment, well, it's not so clearly one way, is it? If X is attached to Y, is Y attached to X? Maybe. Here are some examples. We say that a VPC endpoint is attached to a network interface. The converse doesn't really hold. Network interfaces we visualize them as sort of smaller things, and so, or rather the endpoint is smaller. So the endpoint is attached to the network interface, and it's and we probably, I don't think we'd want to say that the reverse. We wouldn't want to say the network interface is attached to the VPC endpoint. But on the other hand, an IAM user is attached to a policy. So informally, at least, we might say that the policy is attached to the IAM user. The direction doesn't really matter there. And then we get to association, and that really is just definitely a two-way thing, I think. If X is associated with Y, Y probably is associated with X. Security groups are associated with ENIs. Security groups are associated with ALBs. Security groups are associated with EC2 instances. You associate a scaling policy with an auto-scaling group. You associate AWS Shield with a CloudFront distribution. You associate a VPC with a peering connection. So these are all associations. But frankly, if you could probably of course you could just say the word attach in all those cases. So we have containment, attachment, and association. and have put them here in order of increasing mysteriousness. And you can see the documentation for AWS config, which is where they had to think in quite a disciplined way about how resources on AWS relate to one another. Sometimes AWS describes a resource as elastic because it can easily enter into a relationship with another resource and easily leave the relationship. For example, Becky Weiss, the senior principal engineer at AWS at the time of speaking, said that security groups are a simple, elastic container for defining who can talk to whom. That's a description of security groups, a simple, elastic container for defining who can talk to whom. Why is the security group called elastic here? I think it's because it can come into contact, collide, with EC2 instances, and just as easily be detached from them, walk away from them, like with an elastic collision in physics. We have two resources which can be attached and detached from one another. We can see the similarity to two bodies in physics. The association between the two bodies leaves everything as it is. This portability sense of elastic seems to also be present with the elastic block store. The idea is that the EBS volumes can be detached from the EC2 instance with ease, and then attached to another EC2 instance. What about elastic compute cloud? It's not clear that the two bodies are detachable from one another with EC2. Customers own virtual server and own virtual servers and just as easily do not. Is that the idea? Of course not. In EC2, the ambiguity of the word elastic really comes forth, and it's probably a good thing. It's kind of portability, but it's also kind of deformation. Portability. No, portability and autonomy. I mean, autonomy. How could you forget that? Portability, that probably is, the ability to move it about, that probably is the predominant sense when it comes to the elastic network interface. You can create a network interface, attach it to an instance, detach it from an instance, and attach it to another instance. Move it about. It's also found in the elastic fabric adapter. You can detach an EFA from an instance in the same way that you detach an elastic network interface from an instance. And this idea of a transient relationship between two entities is also found in the elastic IP address. You can dissociate an elastic IP address from an instance or from a network interface at any time. After you dissociate the elastic IP address, you can reassociate it with another resource. It's not coherent to talk about an EBS volume, a security group, a network interface, a fabric adapter, or IP address expanding and contracting in the way that a spring does. An IP address has no shape, so it can't undergo elastic deformation. However, these entities can be attached and then unattached, such that things are as they were pre-attachment. If AWS had drafted the act which allows American citizens to carry their health insurance form from one employer to another, it wouldn't have been called HIPAA, HIPAA, but Elastic Health Insurance. Yet it's undoubtedly clear that some people are trying to push the autonomy sense of elastic. AWS have a web page with guidance on their well-architected framework. Most people, when thinking of cloud computing, think of the ease with which they can procure resources when needed. This is only one aspect to elasticity. The other aspect is to contract when they no longer need resources. Scale out and scale in. Scale up and scale down. Some services do this as part of their service. Amazon S3, Amazon SQS, Simple Queue Service, SNS, Simple Notification Service, Simple Email Service, and Aurora. Some require vertical scaling, like Amazon RDS, which means, as opposed to adding more units, you increase the capacity of the individual units, you upgrade. That's what vertical scaling means. Others integrate with AWS auto-scaling, like Amazon EC2, the Elastic Container Service, and Fargate, EKS, and Amazon DynamoDB. So they scale up and down for you. Amazon Aurora Serverless and Amazon Athena also qualify as elastic. Well, with something like EC2 autoscaling, we most vividly have the idea of expansion and contraction. The contraction can be autonomous, since you can essentially program AWS autoscaling. As demand on your servers goes up, a greater number of EC2 instances are provisioned. Then the number of EC2 instances automatically decreases as demand decreases. Well, where are there two resources which are easily attached and then detached? It's not so clear here. So EC2 autoscaling manifests this autonomy sense of elastic, rather than portability. The set of EC2 instances which you have running is analogous to an elastic material which deforms in response to an external force and then returns to its original size. The two senses, portability and autonomy, of course have a central idea, and that's the idea of leaving everything as it is. An EBS volume is easily detached from an instance, and things as they were before are as they were before. Your set of running instances balloons to twice its size and then contracts, and things are left as they were before. So elastic IPs, it's important you note, they are promiscuous but self-assured. And when you hear mention of EIPs, bring to mind immediately the idea of a public IP address. If an IP address is a private IP address, then it is not an EIP. The famous feature of NLBs is the fact that you're provided with static IP addresses. This is done on a per subnet basis. Now, your network load balancer will either be internal or internet facing. If it's internal, you can specify one private IP address per subnet. If it's internet facing, an internet facing network load balancer, you can optionally specify one elastic IP address per subnet. One elastic IP address, they're promiscuous but self-assured. In both cases, you're getting a static IP address. Let's go into this more. The category of static IP addresses cuts right across that public-private distinction. A private IP address can be static. A public IP address can be static. The NLB is renowned because the IP addresses it provides are static, whether public or private. Clearly, then, it is not only elastic IPs which have private static IP addresses. It is true that if you have an elastic IP, then you have a static IP. But it's not necessarily true that just because you have a static IP, you have an elastic IP. Excuse me. So clearly, what I meant to say is clearly then it's not only elastic IPs which provide static IP addresses. Okay, so again, it's true that if you do have an elastic IP, then it is a static IP, but you can't do the converse. Just because you have a static IP, it's not necessarily an elastic IP. Notice that you do not specify an IP address per availability zone. Okay, we talked about an NLB and getting some IP addresses per subnet. So why not? Why not per availability zone? Why would this be undesirable? Remember, a subnet is confined to one AZ. However, multiple subnets can live in an AZ. And we go into a bit of controversy here. Well, sometimes AWS do talk as if you specify an IP address per AZ. In his 2017 announcement, Jeff Barr wrote, "This new load balancer is optimized to handle volatile traffic patterns while using a single static IP address per availability zone." This suggests that if a number of subnets are all huddled together in one AZ, then they are all reached by one IP address, don't you think? In contrast, the following extracts from the NLB user guide suggest that IP addresses are assigned on a per subnet basis. So there's a subtitle that says specify an elastic IP for your load balancer. And it says when you create an NLB, you can specify one elastic IP address per subnet using a subnet mapping. And we've got an example command here. So the actual command is create load balancer. See that? Create dash load dash balancer. And then every time you see dash dash, the double dash, it's a parameter. So dash dash name, the name should be my load balancer. Dash dash type, the type, by the way, should be network. Dash dash subnet mappings, that's the third parameter. They're saying the subnet mappings, well, here's the subnet ID, and they provide a subnet ID. It's subnet dash 0E3. And the allocation ID is EIP ALL, and so on. So here we have someone creating a load balancer. It's a network load balancer, and the parameter is subnet mappings. It's not AZ mappings. Let's have a read of another section. You enable one or more availability zones for your load balancer when you create it. If you enable multiple availability zones for your load balancer, this increases the fault tolerance of your applications. You can't disable availability zones for a network load balancer after you create it, but you can enable additional ones. When you enable an AZ, you specify one subnet from that AZ. Elastic load balancing creates a load balancer node in the AZ and a network interface for the subnet. The description starts with ELBnet and includes the name of the load balancer. So we get two things. We get a load balancer node in the AZ and a network interface for the subnet. Each load balancer node in the AZ uses this network interface to get an IPv4 address, an IP address. Note that you can view this network interface, but you can't modify it. And I've highlighted some crucial bits. When you create an internet-facing load balancer, you can optionally specify one elastic IP address per subnet. If you do not choose one of your own elastic IP addresses, Elastic Load Balancing provides one elastic IP address per subnet for you. These elastic IP addresses provide your load balancer with static IP addresses that will not change during the life of the load balancer. You can't change these elastic IP addresses after you create the load balancer. When you create an internal load balancer, you can optionally specify one private IP address per subnet. If you do not specify an IP address from the subnet, Elastic Load Balancing chooses one for you. And these private IP addresses, they provide your load balancer with static IP addresses that will not change during the life of the load balancer. And you can't change those private IP addresses after you create the load balancer. So they've said you specify one EIP per subnet. And they said here one private IP address per subnet. So how do we make sense of this? Are the famous static IP addresses which you're given with an NLB assigned per AZ or per subnet? The best answer I can give is as follows. There is an unspoken assumption that you desire as few IP addresses as possible. So, having multiple IP addresses within one AZ is not something that anybody talks about. When the documentation above says that you can specify one private IP address per subnet, this translates into one address per AZ, since we can be certain that if your load balancer has targets in an AZ, then there must be at least one subnet in that AZ. In other words, the documentation is not necessarily stating that multiple subnets within one AZ can each have a distinct static IP address. I would hazard a guess that you cannot have more than one IP address per AZ. This is because Jeff Barr states, If you have targets in US West 2A and others in US West 2C, two availability zones, NLB will create and manage two IP addresses, one per AZ. Connections to that IP address will spread traffic across the instances in all the VPC subnets in the AZ. The phrase used is all the VPC subnets. Okay, all the VPC subnets, suggesting that multiple subnets crowded within an AZ all correspond to one IP address. I think that if you assigned elastic IPs on a per subnet basis, one for each individual subnet, including ones within an AZ, then we'd have to say that the paragraph above has been written in a very misleading way, and there's no reason to suppose that. Therefore, I think it is that you are assigned EIPs on a per AZ basis. The paragraph actually says, NLB will create and manage two IP addresses. It settles on two, precisely. So if the principle was one IP address per subnet, then the paragraph would have to mention that there were two subnets in play, but it doesn't. I conclude that one per AZ seems to be the principle. That is, it's not just a fact that happens to be the case, because there happens to be just one subnet in each AZ. The principle is that it's one EIP per AZ. Well, that's my argument, my interpretation of it anyway. So it's linked not to this network concept, this subnetwork, this sort of logical construction, but it's actually linked, the provision of the EIPs is linked to the physical construct, which is the AZ. If there were 5 subnets in each availability zone, in that example used by Jeff Barr, 5 subnets per AZ, Jeff Barr would still say 1 per AZ. Because his point is that the connections to that IP address will spread traffic across the instances in all the VPC subnets in the AZ. So one IP address corresponds to many things in the AZ, and he's talking about many subnets. So this just wouldn't make any sense if it was one EIP per subnet. We can also note that the documentation states when you enable an availability zone, because that's what you do, you have to set up the load balancer for a particular availability zone. You specify one subnet from that availability zone. Elastic load balancing creates a load balancer node in the availability zone, a load balancer node, and a network interface for the subnet. And the description starts with ELB net and includes the name of the load balancer. Each load balancer node in the availability zone uses this network interfaces to get an IPv4 address. So, one subnet in each AZ is singled out. We set up base in one subnet. One subnet is used to house the load balancing equipment. It has a network interface within it. This network interface imbues an IPv4 address upon anything in the AZ, including things in distinct subnets. If the principle is truly one IP address per AZ, then why did the user guide talk as if it was one IP address per subnet? The answer is that the means by which we establish one IP address per AZ is by placing a node in a subnet within the AZ. And so that's why they spoke in a bit of a misleading way and said it's one IP per subnet. That's my understanding anyway. Note that both the ALB and NLB have a client-facing DNS name. A DNS name. Each network load balancer receives a default domain name system name, and it has the following syntax: name-id.elb.region.amatzonors.com. That's how I pronounce that. For example, my load balancer -1234.elb.useast2.amatzonors.com. There are 5 segments in the DNS name of an NLB. Take a look at these steps written out to test your load balancer. 1. After you're notified that your load balancer was created successfully, choose Close. 2. Under Load Balancing, choose Target Groups. Choose the target group. 4. Choose targets and verify your instances are ready. If the status of an instance is initial, it's probably because the instance is still in the process of being registered, or it has not passed the minimum number of health checks to be considered healthy. After the status of at least one instance is healthy, you can test your load balancer. 5. In the navigation pane under Load Balancing, choose Load Balancers. 6. Select the newly created load balancer. 7. Choose Description. So each load balancer has a description, and copy the DNS name of the load balancer. For example, my load balancer .elb, which is in the US East 2 region, which is in Amatsu North, which is in the commercial domain. Paste that DNS name into the address field of a web browser. If everything is working, the browser displays the default page of your server. In other words, you go to the name of the load balancer, and that's how the load balancer then takes you to what's behind it, the server that's behind it. So let's clarify a few things. Will this domain name resolve to the IP address of the targets? No, it will resolve to the IP addresses possessed by the load balancer. Your load balancer has IP addresses associated with it. Its targets have their own IP addresses. Clients, send traffic to the IP address of the load balancer. A 2021 article by Gamal Eldin points out something useful. We know that the NLB will have a name that resolves to multiple IP addresses. We just established that it was one IP per AZ, for example. It's linked to the physical AZ. Again, these various addresses are the NLBs, not the target IP addresses. We know that the principle is one IP per AZ. Therefore, if we can direct traffic to one of the IP addresses in particular, one of the ones belonging to the NLB, we can direct traffic to one AZ in particular. And we might want to do this, since we might want to limit cross-AZ traffic. Gamal Eldin writes, the load balancer has DNS records for each of its nodes. You use these DNS names, along with the following syntax, to determine the IP addresses of the load balancer nodes. az.nameid.elb.region.matsunorth.com. Notice how there are now 6 segments in the name. We put the AZ name as the first segment, and that's why there's 6 now, not 5. Again, we're still sending traffic to the load balancer, and the load balancer is still balancing the traffic for us. We're not, for example, bypassing the load balancer and sending traffic straight to the target. But we're using a specific variation on the NLB's name to limit the targets to which it distributes our traffic. See Gamal Eldin 2021 for a full explanation. Link in the description. Who sent you? Often notes on AWS which are discussing the load balancers on AWS simply mention X-forwarded for header and proxy protocol without explaining what those things are. What these two things have in common is that they are concerned with preserving some way of identifying the source IP address, despite the middleman, right? Despite the load balancer. But how do they differ? The story starts in Boulder, an American city famous for the Flatirons. These are mountains. Boulder is often referred to in the tech industry as the Silicon Flatirons, analogous to Santa Clara Valley's famous nickname. So it's a city called Boulder. The great views of the landscape in Boulder have been preserved. In 1976, a policy was announced called the Danish Plan, and it was written by a man called Paul Danish, and it put strict limits on the number of new properties that could be built each year in the city. For example, growth in properties would be about 1.5% a year. Boulder is in the US state called Colorado. One building in particular which was given planning permission is the headquarters of NIST, the National Institute for Standards and Technology, and it's important that we briefly stop by here. The campus for the National Institute of Standards and Technology, it's in the city called Boulder, which is in the US state called Colorado. The National Institute of Standards and Technology was established in 1988 by Congress to assist industry in the development of technology needed to improve product quality, to modernize manufacturing processes, to ensure product reliability, and to facilitate commercialization of products based on new scientific discoveries. 1988, 1 year before we say usually that the web began. NIST, originally founded as the National Bureau of Standards in 1901, works to strengthen US industry's competitiveness and advance science and engineering. NIST is responsible for the Federal Information Processing Standards, FIPS. The one which you'll see a lot of in cloud computing is FIPS-140. This concerns cryptographic modules. FIPS 140. The first version of FIPS 140 was published in 1994. However, there's a whole variety of publications which are part of the Federal Information Processing Standards. Information processing is quite a general term. Computing carried out by machines can count as the processing of information. But perhaps paperwork manipulated by humans or transported using telephone lines, can that count as information processing? We know about the distinction between parallel processing and sequential processing. Federal simply means relating to the US government, specifically the central government, as distinct from governance at the state level. So we have lots of different ones. FIPS 153, that's to do with computer graphics. FIPS 197, that's also known as the Advanced Encryption Standard, published in November of 2011. FIPS 137, this is a speech encoding standard. It contains rules for secure telephones. This was published in 1988. However, it was actually converted from an older NATO standard, STANAG 4198. We have FIPS 199. It requires federal agencies to categorize their information. The 3 categories: confidentiality, integrity, availability, or CIA. There's FIPS 140. What is that relating to? And so we have documents like this. So it says federal at the central government level. Federal Information Processing Standards publication. This one's from 1987. This is to do with intelligent peripheral interfaces. Peripheral meaning on the side. It's to do with hardware. Is that things like mouses and keyboards? So this opening paragraph always explains that the reason they're devising the standards is that some law has been created by Congress, and now NIST needs to come up with standards that help organizations to be in line with the law. So it says the Federal Information Processing Standards publication series of this National Bureau of Standards is the official publication relating to standards, guidelines, and documents adopted and promulgated under the provisions of Public Law 89-306, the Brooks Act, and under Part 6 of Title 15, Code of Federal Regulations. These legislative and executive mandates have given the Secretary of Commerce important responsibilities for improving the utilisation and management of computers and automatic data processing in the federal government. To carry out the Secretary's responsibilities, the National Bureau of Standards, through the Institute for Computer Sciences and Technology, provides leadership, technical guidance, and coordination of government efforts in the development of standards and guidelines. James H. Burrows. So these standards are really quite old. Federal Information Processing Standards. Above you can see such a standard from the 1980s. This one is for cryptographic modules. The specific standards concerning cryptographic modules, FIPS 140, began in 1994. Then, in December of 2002, FISMA was enacted. Now, of course, NIST already has standards with information processing in their name. So why do we need FISMA? FISMA is a very wide-ranging rule, so the name needed to be slightly more general. That is, FISMA does not merely cover the processing of information. However, it does tend to limit itself to security matters. It's really about the general task of the management of information security. Also, note that FISMA is a law. FIPS are standards. On 17th of December 2002, George W. Bush signed the Federal Information Security Management Act into law. This is the Federal Information Security Management Act. FISMA. FISMA has charisma. Everything wants to be part of it. That is to say, roughly, FISMA tends to encapsulate other laws. Other laws you will come across will tend to be after FISMA, because FISMA was signed into law in December of 2002. Which is quite recent, relatively. Now, AWS is usually said to have begun in 2006, although the Simple Queue service was put through beta tests in 2004, from 2004. It's around 2010 that US lawmakers started thinking about standards relating to cloud computing in particular. Private companies and federal agencies were ramping up the amount of data stored and processed in the cloud at breakneck speed, or rather, they wanted it to be at breakneck speed. The move to the cloud was in fact being limited. All-encompassing FISMA with its charisma was rigorous and comprehensive. Any company which wants to sell its services to a federal agency, federal meaning accountable to central US government, must be authorized to do so. Laura Taylor writes, "The authorization process is extremely comprehensive, and until FedRAMP came along, system owners had to go through the entire authorization process for each federal agency using their system, even if the system was exactly the same from one agency to another." Prominent in the birth of FedRAMP was Vivek Kundra. If you're not aware, Vivek Kundra was the first Chief Information Officer of the United States. This was a new office. Barack Obama appointed Vivek Kundra on March 5, 2009. Kundra was to play a key role in making sure the US government is running the most secure, open, and efficient way possible. According to Taylor, Vivek championed cloud adoption as a way for agencies to save resources and improve service. At this point, however, this really was merely a target. The assumption is that the cloud will only be adopted by federal agencies if it is officially secured and vetted. Cloud adoption would be very slow with the time-consuming and extensive FISMA authorizations that had to occur. Ultimately, the Federal Cloud Computing Working Group was set up and chaired by Peter Mell. Mell worked at NIST. It's in Colorado. FedRAMP, Federal Risk and Authorization Management Program. So the Fed is for federal. So risk, we're managing the risks inherent in a technology, and that goes back a long way. The cloud is just another example of a technology. Authorization, as in your company is now authorized, allowed to sell your product to insert federal agency. Authorization is allowing people to do things, permitting them to do things. It's not the same as authentication, which is about identifying people. So the RA is for risk and authorization. Note that the authorization of a system was possible. You're authorizing a system to host federal data. The problem was that the authorization was limited to individual federal agencies. The working group headed by Peter Mell was aiming at some sort of government-wide authorization. This would mean that if a company was authorized for one federal agency, they'd be authorized for all federal agencies. Also involved in the effort was Katie Lewin and Casey Coleman. Around early 2010, it seems that while Peter Mell was enjoying a snack, the acronym FedRAMP, Risk Authorization, FedRAMP appeared on a paper plate next to Mell's sandwich. I believe this is because they were brainstorming, writing words on paper plates, not because there's a paper plate company in Maryland called FedRAMP. Peter Mell and Katie Lewin went and pitched the idea to the US Chief Information Officer, Vivek Kundra. By December of 2010, Kundra published a 25-point implementation plan for cloud computing. The plan announced the Cloud First policy, which stated, when evaluating options for new IT deployments, the Office of Management and Budget will require that agencies default to cloud-based solutions whenever a secure, reliable, cost-effective cloud option exists. I've emboldened these adjectives, secure, reliable, and it seems we've stumbled across an explanation for these adjectives reliably accompanying every product description. So we're now a little bit more clear on the distinction between FISMA, signed in, December of 2002 by George W. Bush, and FedRAMP. FISMA is a very general act concerning various matters related to information security. FedRAMP specifically concerns cloud computing. The Federal Information Security Management Act was first signed into law in 2002. The FedRAMP policy was signed in 2011. FedRAMP is a specific application of FISMA. Taylor writes, FedRAMP is the US government program to apply the Federal Information Security Management Act to cloud computing. FedRAMP is generally regarded to have been very successful, and governments in East Asia and Europe are pinching the idea. We've just looked at some laws and some standards. Laws and standards are different. Laws are created by legislative bodies which are part of the government. An example of a legislative body is the United States Congress. Standards, meanwhile, are developed by government agencies. The standards help individuals and corporations to implement laws. An example of a government agency is NIST, the National Institute of Standards and Technology. FedRAMP and FIPS 140-2 are two examples of standards developed by this government agency, NIST. The US Congress cannot create a law on its own. The US President must sign the bill. We'll continue this next time.